Hello, welcome everyone. I'm joined by Bruce Fuda, and we're going to talk about digital technologies. Bruce, are you there?
Hello everyone. I'm welcoming you from Canberra, the nation's capital, and I'm looking forward to joining you for today's discussion on data representation in the digital technologies curriculum. So it's going to be one of a series of unpacking the curriculum webinars that we're going to be doing. And we encourage all of you to ask us questions using the Ask a Question button at the bottom of the screen there. And feel free to discuss anything that we're saying or to throw your own comments and thoughts out as we go in the chat window on the right-hand side.
Heckling is always encouraged.
Nicky and I are always happy to respond to any of your concerns or to challenge us if we say something that you think you'd like to make some comments about. So we're going to switch the screen over now to the slide that they're front and center. And as we move through, Nicky's got control of the wheel. As we move through, both of us will be taking the lead in discussing various things. So Nicky.
Actually, I think before we get started, you should introduce yourself and take some responsibility for what we're actually going to be talking about as well.
Okay. Actually going to be starting with a quick overview of where things are in the curriculum. I was one of the writers of the Australian curriculum. I worked with the rest of the team on getting this up and running, and it's in the state that it is in when it's implemented in your schools. Now, I know for some of you who are coming in from other jurisdictions around the country, you'll be working with your variant of the curriculum as published by your state curriculum authority. However, all of them have been written on the basis of the content in the Australian curriculum, and for that you can blame the rest of the writers more so than me. I joined the team a little bit later on. But let's get started with a quick overview. So,
all right.
Nicky?
Okay, I will focus this screen and we will get going.
Now, for people who have been to a workshop with us before or who have had an opportunity to go over the curriculum in detail, one of the things that makes this curriculum, this subject different to a lot of the others is that it's written around a series of key concepts, and those concepts were chosen because they are concepts that have been true since the dawn of computing and will continue to be true in the future. And what we'll be focusing on for this webinar is data representation. Now, if you want additional information about the other key concepts and a more detailed curriculum overview, we do provide that in our workshops, and we have a webinar that was published a couple of weeks ago that also covers some of this in more information. So what we're focusing on is actually one of the strands, one of the elements of the knowledge and understanding strand in the curriculum. So back to that, Nicky. And what you'll see when we bring up the curriculum overview in just a moment is that all of the data representation concepts are captured through a single sequence of learning in a series of content descriptions. So Nicky will bring up the next slide there. The curriculum is available as a downloadable PDF Australian curriculum website, and it's all key concepts, and you'll see on that first page that Nicky had up just a little while. Data representation runs across the second row of the PDF on the first page, just there. In Year 9 and 10, it also includes something a little bit further down on the next row, but ultimately that's how you understanding the progression of data representation in the curriculum from kindergarten up to Year 10.
So we really like this overview that has the different bands and how a particular concept is built up bit by bit, and how that works. And it's especially useful for the next few years when you've got students who are coming in perhaps at a year level where they don't have, or they haven't been learning from foundation, from kindergarten all the way up, because it gives you a good idea of where to drop them in and where the complexity increases, but that same concept is explored.
Okay, so you'll access the PDF on the Australian Curriculum website. You'll find it in the Understand How Technologies Works section of the page. And the PDF document you want is the Digital Technologies sequence of content. Now, it is hidden behind a collapsible expanding button. So that's a plus. You click on that, it'll expand and you'll be able to access those PDF documents there. The curriculum website's great for many things, but the one thing that the standard view doesn't show you is that relationship between the different and the individual concepts. So we really recommend that you grab a copy of that PDF so that you're clear on how the content descriptions between levels are related to one another.
If you're looking for it as well, we'll tweet it out at the end of this webinar as well, probably along with the slides that we're using in this workshop webinar. Cool.
That's right.
All right. So talking curriculum.
So yeah, the curriculum was written by a team with over a period of about sort of 9 months, and a lot of discussions took place in that time. And the curriculum document that's printed needs to do is capture all of that and pack it up into a document that makes sense. Everything that we've written. Of course, the challenge with doing that is that there's a whole heap of stuff that is very difficult to include. And when we do pack things up, the challenge for you then is how you're going to unpack it so that you can actually teach the thing. And that's sort of what these webinars, the workshops we run, and all of the other activities that we're going to be developing over the next little while are all about. It's to help you unpack everything that we discussed so that you can deliver on that curriculum when you're back in your classrooms.
Hopefully these webinars will make it a little bit easier to wonder, so you won't spend the next 10 years wondering what on earth Bruce and the rest of the team meant by this particular dot point. Or at least if you do, you have an opportunity to ask. Now is a good opportunity to ask.
That's right.
So we're going to start with data representation as our thread, as the theme of this webinar, and we'll do the other concepts along the way as well over the next several weeks, I guess. Yeah, so
I'll introduce the topic. Data representation is defined in the Australian curriculum in the structure of the Australian curriculum section, and this is the definition straight from the curriculum document. And what we're focusing on is how data is represented and structured symbolically for storage and communication by people and in digital systems. And I think the thing that we really want to focus on is the by people element. It's very easy when you're teaching digital technologies to get very caught up in the technical computer stuff. But I think what's really, really critical to understand the role that digital technologies has played in the shaping of our society is that you focus on that element of people. And that's what we're going to do with our introduction here to data representation. So I'll let Nicky take over from here for a little while.
So what we're going to do is look at things, look at the curriculum as it builds up. So we're going to start looking at what the curriculum outcomes are for Foundation Year 2. Yes, sorry, secondary teachers, that means you've got to sit through a whole bunch of other stuff, but it'll be really useful and pretty fun, hopefully along the way as well. So in Foundation to Year 2, the main outcome as relating to data representation looks at recognizing, exploring, and representing data. So this could be looking at pictures, symbols, and diagrams, and that's what we're going to start with. Oh no, my emoji. See, this is what we need emoji support for. Data representation, it's everywhere. Okay, so everyone at home, what we would like you to do is grab a pencil and paper or pull up Paint or Snapchat on your phone, whichever you want. And what we'd like you to do is draw a pig or a dog. Either way, whichever one. And we're going to ask if there are any volunteers who want to show their drawings in a minute. Otherwise, I have a few that I prepared earlier on good old Post-it notes. So what we're doing here is talking about how do we represent concepts. So draw a pig, draw a dog, don't label them. We're going to press on. Yeah, let's press on. Unless anyone... There's no heckling in the chat. Has anyone got a pig or a dog? Silence. I think
that's all right. We'll keep going.
All right, so in the meantime, while you're preparing your representations, we're going to talk about some good representations and some bad representations. So this is a no. I think it's very clearly a no Trojan horse representation is what's trying to be conveyed here. This is a sign very nice, Jess, yes. Jess has just sent through the emoji pea face. This is a sign at Perth Airport. But clearly to me, the ear angle, it really looks more like a horse. I think it's the neck that does it. The fact that it's a commonly understood concept, as in don't bring dogs into buildings generally, helps get away with this. But what are some, we want to think about what makes a representation good and what makes a representation less good. So to me, this one could be improved by a few small factors. Specifically, I really like the inclusion of a collar here, and the fact that the dog's ears are sort of more upright. To me, a lot more doggy-like. Other people are perhaps more lenient than I am, and they say that they're both perfectly fine representations of dogs. And then I show them things like this one. So I've heard a lot of different interpretations of this particular sign. This is a street sign seen in Maruya. We're getting a lot of echo and both mics are on. Bruce, do you want to mute? Good, cool. So this is a street sign near Maruya. And it is very clearly saying to watch out for two-headed cassowaries on the road up ahead. That's how I interpret that. Someone has also, I've also heard that it's a watch out for turtles riding emus. Watch out for giants on bicycles to your left. Deb has it. Nice work. No falling on cars. That is actually what this sign is warning you about, sort of. I think it's kind of like flying children as well. Yeah. So this, in Maruya, a frog. Ooh, that one's good. In Maruya, there's an airport. And at that airport, people go skydiving. This is a representation, perhaps I use that word generously, saying watch out for skydiving in the area. Now, if this is actually what we're trying to talk about, skydiving, or at least warn you of, how could we prove this? This is the sorts of conversations that you want to be having in terms of data representation that you could in fact have with young kids. What does one represent skydiving generally? Well, I would hazard that perhaps if we're trying to represent skydiving, we should represent a successful skydive, one in which the parachute is actually deployed, be quite useful. So to me, I would want a parachute, a skydiver with a parachute. I really don't know why there is a giant on a bicycle to the left of the car. I mean, there's a lot of unnecessary information in this slide. In this sign that we already know we're driving. Hopefully, we haven't forgotten that. Although perhaps that's the point. It's while you're busy watching a skydiver, hopefully not plummet to their death. Watch out for swerving into the giant on a bicycle to your left, because don't forget that you're in a car. It's rather confusing. A lot of really good examples of slides of signs around various neighborhoods that we've had dobbed into us by teachers. If you're in an area that has some dodgy signs, this is a great way to spark your students' engagement as well. So there tend to be a lot of dodgy duck signs, duck crossings. That seems to be a particularly rich vein of inspiration in these. But when we're generally talking about these signs, what we want to be doing is having a conversation about communicating some information. So whether this representation communicates that information adequately or not. And so you've all had a bit of time. I want you to look down at your pig and at your dog and think about whether they adequately represent or convey that information. And we're gonna play a little bit of show and tell. I'm gonna hold up a few to the webinar, and you've got to guess what you think this is. These are actual, I'm going to wait until someone in the chat guesses in. These are actual examples that we've collected from some of our workshops previously. Here's one of them. All right, everyone's gone quiet. I think you're all scared. That one was my video's gone off.
Yeah,
oh, no.
Nicky, we've lost you. Well, some of us have at least, yeah.
Well, that one was a dog. Deb got it. For those of you who can still see me, we've got an image. Well, yes, no, maybe a pig. Hang on 1 second.
So while Nicky's sorting that out, one thing that I think is worth mentioning is that whilst this is something you can introduce with students at a very young age, the discussions that you can have with older students around this are really, really valuable. So the concept of data representation is absolutely fundamental in all year levels of the curriculum. Just because we're talking about it in the context of introducing it with the very young students, it doesn't mean you shouldn't be having these discussions with all types of representation later on. Understanding which bits of the data are important, which bits are unimportant, what are the elements you should be focusing on, those are all really valuable discussions that you'll have with students at every age. And in fact, they're critical to discussions with students in the older years when we get to things like compression and understanding how data is structured. So one of the things we really try to do when we introduce the topics in the early years is we try to make it very, very clear to teachers of students in the older years that you can have these discussions, but that you'll be incorporating some of the other things we'll talk about later in the webinar. And that's to ensure that you don't feel like what we're doing right now is of no value to you. We really want to make sure that the whole discussion we have tonight is going to be useful. So,
all right.
Let's
pick the router. I just want to show you one more pig and dog. Just for those of you who are close up, if you can see that one, here we've got some sort of an animal with spots. It's got spots. And given what we know about how we generally represent pigs and dogs, we can have a pretty educated guess that had, I think it looks like some sort of a cow cat. Yes. But it doesn't have the things that we usually associate with pigginess, that those being snouts and curly tails. So it's probably the thing that's not a pig, which in this case, other than a cat-cow, is a dog. All right, so what we're really talking about here in this general discussion is representation. And this whole point of having data representation is so that humans can communicate better. So this is partly thinking about sort of the purpose of human existence in some sense is to communicate, but it's also thinking about having thoughts, being able to create this knowledge. To a lesser extent then, or in terms of importance, it's being able to manipulate information and do calculations and analyze that information. And then also to an even smaller extent in terms of the importance to humanity is storage. So this data representation as a means of storing information so that you can transmit it both across continents and into the future. So if we think about how we've saved information from the past, and we've used that in more than just history classes, then that's the sort of thing that we use data representation for more generally. So the point of this all is to help humanity. So this is going back to that by humans, for humans. This is a use. Data representation is hopefully a useful thing. So if we want to trade a pig, trade has historically been a huge driver of human improvement, you could say. So I could take my pig down to the market, and that's all great. And it's kind of annoying when there's one pig, but it's very annoying when there's more than one pig. It's very annoying when there are 30 pigs. It's just not useful. It's not practical. So we need a better way of actually representing this pig. What we could do is, in a happy world where we all speak the same language, I could go down to the market and say, hey, I want to trade 30 pigs, and have the other person be able to understand that and communicate. But until I've invented language, it's very difficult to do that, or if perhaps the other people don't speak the same language as I do. So historically, communication has been limited by things that I could see directly. I'd have to drag all 30 pigs down to the market. And then the next step of communication up, this next step of representing that data in terms of a little bit more complicated but still quite useful, would be take a part of the pig that represents a whole. So this concept that this small part of something can represent something bigger is actually quite complex, but something that we're thankfully quite good at. So it takes, the skull is quite a good representation, but the skull is tricky if you want the animal to still be a functioning animal. So perhaps you could take those pig tails that we talked about before as salient piggy features. But maybe after a little while, those bits get a little bit smelly or inconvenient. So then we want to take another step in abstraction level and have some way of representing this using a painting or a symbol, perhaps for just drawing a curly tail in the sand. At the same time, sounds and language are developing, and from there we eventually get symbols happening, and that is the birth of language. So now we have a way of depicting information in a physical form using symbols, and also representing that same content, that same those same concepts using sounds. Kim's pointed out that data representation would almost always be contextual. So it doesn't matter how good a car picture was if the person has never seen a car. And absolutely. So if someone has never seen a pig, and I try and describe this, there's this thing, that the thing that has the curly tail and the snout, we're going to have a terrible time. But if I know that the person has an understanding of what I'm trying to convey, I can use these shortcuts to leverage that information and reduce my complexity of the data representation that I'm actually transmitting to actually make sure that you understand the content that I'm trying to convey as well. So we'll go back to our pigs. This is a pig in Sulawesi in Indonesia. I've just got another relief picture of that pig. So you can see that 35,000 years ago, more than, we have a drawing of a pig on a cave wall, which really isn't that much. It shows that perhaps art education hasn't improved much in the last 35,000 years, but it also shows that we've been working on this whole data representation thing for a long time, and that these symbols and these symbolic representations are something that we're now quite good at interpreting.
And so I think that's a really good opportunity for us to say that one of the concepts that doesn't actually live on its own in the Australian curriculum is that of abstraction. And the reason is that abstraction is actually a kind of fundamental concept that is a part of every element of digital technologies. It presents itself through data representation. It presents itself through algorithms and through the implementation of digital solutions. And so we're going to talk very briefly about abstraction here, but we just want you to know that it's a concept that ultimately is going to allow you to determine the level of detail that you're going to be discussing these things with students at, and exactly how that progression from foundation up to year 10 will look. So a quick definition: abstraction is all about hiding details that aren't relevant so that we can actually focus on and manage the appropriate number of aspects for solving a problem. We do this naturally because often in a discussion, and if you think about the way that you greet a very close friend versus an acquaintance, normally the sort of small talk response to how are you going is something like fine. when you don't know the person very well, whereas a close friend, you may go into a lot more detail. And that's because as far as the acquaintance is concerned, they're not familiar with the details of your life. That extra information is of no relevance to the conversation or the interaction that you're about to have. So one of the things that we're really going to focus on for the next section, and that you'll see as we move up to the Year 9 and 10 level of the curriculum, is that as we become more familiar with these concepts, we begin to peel away some of the layers of abstraction and start talking in more detail about some of the more complicated ideas. So this is one way of representing a pig in the modern era. Nicky? You're muted, Nicky, so I can't, I have no idea what you're saying.
It was about imagining things, so I guess it's moderately relevant. So if you all imagine that image of a pig, you've got that good mental image of a pig, hold tight to it, imagine it. Does it look like this?
And so you'll notice that if you look at Pepper, she's got a lot of the features that we would see as being piggy. She's kind of round, she's pink, she's got a curly tail and a flat snout. All of those features scream. I mean,
she's
pig,
also wearing a dress.
And it doesn't matter. She's wearing a dress and she's got a smile on her face and eyes that don't look particularly piggish, but she has the features that let us know that she's a pig. And if we look at a more extreme example again, the pig from Angry Birds doesn't look much like a pig at all. I mean, pigs' eyes don't
bulge,
goggle out of their head like that. Pig ears are not that round and sort of perky, and pigs are also not green.
Yeah, I would suggest that most pigs, in fact, have a body or legs.
And so the roundness and the fatness that is implied by this drawing and the snout are really screaming at us that this is a pig, even though it isn't an accurate representation of, an accurate...
Are you trying to say that the Angry Birds pig is not an accurate representation of a pig there?
That's exactly what I'm saying, but it has the features we need. And so a lot of the detail that would be captured in a photograph, such as the hair on a pig's back, is not relevant for us to actually identify exactly what a pig is.
It's got hair in this one. All right, but this one's green. So we've got pigs. And so just to sum up here, what we're not saying is that you can tick off all of the data representation requirements from the F to 2 band by playing Angry Birds, but you do you. You run your classroom like you'd like, but there are aspects of data representation that can be found in particularly unlikely places, perhaps even Peppa Pig, even those unlikely post-it note games. So we're going to press on to years 3 and 4.
We will. And when we move into year 3 and 4, the main difference or the main concept that's introduced or idea that's introduced is that when we're working with data, we can take that same data and represent it in many different ways. And you can see that to an extent, we've kind of begun exploring this already with our pig example there. So Pepper and the Angry Bird pig are both representations of pigs. It's the same data. We've drawn it in different ways. But we want to go a little bit further than that and look at it not just visually, but in terms of some of the other ways that we might represent data as well. So when we, Nicky? Yep. When we start thinking about how humans develop language, one of the things that that Kib mentioned earlier, which is context, one of the things that we really have to understand is that these sounds that we use in our language have been developed by humans. And I think one of the things that we want to emphasize when we talk to our students about the digital technology subject is that it is created by people. It's not some sort of magical thing that was developed and gifted to us and then we learned how to use it. It has developed over time, and people just like them have ultimately been the people responsible for the development of the language. And the language itself is really just a sequence of arbitrary sounds that represents a concept or an emotion that people have agreed upon. In English, we use per, I, g, and we put those 3 sounds together to form the word pig And when we say pig, we mean, you know, the pink round animal that we've been talking about up to this point.
I think you mean the green round animal, definitely.
Or the green round animal, yeah. And so that's just an agreement we've made. You know, we could get together as a group of, you know, 40 odd people that are here right now, and we could say, we're going to use this sequence of sounds to mean this thing. And as long as we agree that that's what we're going to use, that becomes part of our vocabulary. And as long as we all accept that convention, we can communicate an idea using that agreed upon.
And I mean, that's what's happened in languages. That's why we don't all speak the same language. We've all, each society, each language group, linguistic group has developed a different set of arbitrary sounds to represent concepts. That's what makes language fun.
And it's funny because if we then think about the concept of onomatopoeia, where we're taking language to the point where we're imitating the sounds through the words that we're producing, even then we don't agree across languages. So you would think that if we were going to be sort of writing out the sound that an animal makes, we would all hear that sound the same way. Clearly, the conventions of our languages and the way that we familiarize ourselves with the environment in which we live and the sounds that we hear means that we end up with different expressions of those particular sounds. And we don't agree across languages. So English is oink, oink, and, you know, arguably that's not a particularly good version of the noise of the pig.
But it is a fun one. I think the Germans have it pretty nailed with Konz. As one of the co-founders of Grok Learning, I am a little concerned about the Indonesian sound a pig makes of grok. But actually, I've heard some other fantastic ones as well. So apparently in Japanese, pigs go boo boo, which I think is delightful. Just delightful. So I like bringing it back to this thing where we say, well, we've all learned at school, or at least had the discussion with English teachers, that onomatopoeia is a direct representation. This is language imitating sounds. But even when we do that direct imitation, we bring our own understanding of that that sound with it. We represent it differently. And I just have to make a plug for James Chapman's delightful international sound animals. They're fantastic. We'll shoot the link around as well. So this is an activity that I like doing in the classroom, where you ask your students, who often come from a diverse linguistic background, whether they know any other words for the word for wolf or other sound animals in their own language. And you can also add in a bit of discussion about Indigenous languages there as well. So there are some fantastic words for the sound that bees make, which in Warlpiri is very, very different from buzz, but has a similar sort of, I'm just going to linguistic geek out for a bit and talk about fricatives unless you continue, Bruce. So let's push on.
Yeah, we should definitely push on. We've still got a lot to cover. So one of the things that we then look at is if we look at spelling, which is a sort of it's the progression from language back into symbols for storing a lot of the knowledge that we have and things like that. We spell and form the words that we write using a convention or series of patterns that provide additional meaning. So if we want to take walk and we want to make it past tense, then we would add ed on the end to make the word walked. And we do that with talk as well, to get talked. But if you do it with speak and you go to speak, and that's just this application of a convention, you're following the same pattern you have with everything else, then you produce something that's incorrect. And it's not incorrect because you're not communicating the concept correctly. It's incorrect because that's different to the convention that we have all agreed upon. We have a vocabulary, we have grammar rules, we have spelling conventions, and being able to speak in society following those conventions is what's critical for you to unlock the clubhouse and become an active member of society. And it's just a convention. And I think that's the thing that's really, really interesting. And so when students get something wrong, when they, you know, write, speak, and they get marked wrong, I think it's worth having that discussion that, you know, it's not wrong because they haven't communicated the idea effectively. It's wrong because they haven't learned the convention that we have applied for a word of its type. And so a lot of these exceptions are just learning new rules or new conventions and understanding how those patterns apply. English is a stupid language for it, but, you know, it has its roots in multiple languages that all have their own rules. And so it's, you know, partly a result of history and linguistic development in the language that's gotten us to this point. But it's just a convention.
It's true. And
it's no hard
you know, just to language geek out a little bit more, the reason that speak does not go to speaked is because it instead inherits from a different rule, as Bruce alluded to, that it's inheriting the way to form a past tense, not from the French grammar rules, but from the German grammar rules, which involve a vowel change. So really, either you have to learn a whole bunch of arbitrary rules or just learn all of the languages to understand why these things are happening. I'm obviously showing my cards that I like the second option more, but I will talk about language until the cows or the pigs come home. So let's talk about numbers for a little while instead. But we're still talking about pigs. So,
and go, Nicky.
So going back to that trade. So it's a good question from Kim here. How does this relate to the digital technologies curriculum? Is it to show kids that everything is just a convention? It's to show this whole rant, other than the fact that I like talking about languages and numbers and things, is to show that the data representation, the way that we draw pigs, the words that we use to describe pigs, the ways that we talk about the numbers of pigs that we have, or whatever, it doesn't actually have to be pigs. These are all conventions that we've agreed upon and that we as humans have created. And these things seem natural to us because we're familiar with it. But when we go to this next level, which we will do soon, I promise, just as soon as I stop ranting, is talking about binary and other things that don't seem as normal and natural to us, but that are nevertheless ways that humans have developed of dealing with, of representing information, representing data, so that we can manipulate it, so that we can store it, so that we can use it to have thoughts. We want these discussions to be sort of co-curricular, because realistically in the primary space, you're not going to have much time to devote to digital technologies in and of itself, and you'll be forced to look at data representation as part of other subjects as well, or in collaboration with them. And using those concepts to get kids familiar with things that they already feel confident with will hopefully then ease that transition into talking about binary with kids. So hopefully that answers some of these questions, but otherwise we will get back to it at the end to really tie it all up. So let's talk about how we represent numbers. So we can represent numbers using actual digits, but how have humans historically developed this? This is something that we have actively figured out how to do. So if I were taking a pig to market, I could take the 30 pigs, but that's really inconvenient. I could use a tally system to show how many pigs I want to trade. And that might be just drawing lines in the sand, or then the next step would be to draw each group of 5 so that I can easily count up how many groups. Using these things are also students get very confident with them. But then we've developed using our fingers and toes to count. Then we look at using tallies to count. And then we look at the number system that we use currently, the digits that they're hopefully very familiar with, and that this is actually also a system. That this Indo-Arabic base 10 system that we use is a convention that we've all agreed on. So if we look up how the number 103 is formed, what this actually represents is 1 times 100 plus 0 times 10 plus 3 times 1. And if we take that apart, then hopefully students will start to see parallels between not just data representation and what they use on a day-to-day life, but also understand a little bit more about how maths works, how numbers work. The Indo-Arabic base 10 system is what we generally use for numbers, but it's also not the only maths counting system that we use. So some of you might, in fact, I'm going to give you a second to think of another one, if you think of things that students, not struggle is a strong term, but they might be wondering why is it this way? Why does an hour have 60 minutes in it? And why does a clock have 12 numbers in it? Why does a day have 24 hours in it? Why do angles have 360 degrees? These are all different number systems. We've inherited them from different number systems, both the Mesopotamians and the other one escapes me, but we've inherited, thank you, Babylonians, always the Babylonians. We've inherited these other number systems, and understanding why they exist help us both realize that this is not something that has been true since the dawn of time. This is something that humans have created, and this next abstraction level, so to speak, into binary is also something that humans have created as a way of using, as a tool to use.
Okay, so one of the things that you'll find from here on, I'm conscious of time, we've got about another sort of 20 minutes left. We are going to, from this point on, start sort of building on those concepts that we've talked about up to this point, but we're going to do so by pointing you to activities that take these concepts, bring them into the year levels that we'll be discussing, and then provide you with scope to extend further up all the way through to year 9 and 10. So from year 5 and 6 on, we're at the point now where we're looking at data as whole numbers, how we need to be able to convert everything to a number for storage in a computer. And the easiest example for us to begin with is text. So in a computer, what we need to do is take the character that we're going to store, and so that can be letters, digits, punctuation, anything really, and agree on a numerical representation for that character. And this is a relatively new idea. Nikki's put some numbers on the screen. And if you look at that, I'm going to let you have a bit of a guess in the chat as to what you think that might be. But she's written 5 numbers up there: 8, 5, 12, 12, and 15. So what do you think she's represented with those 5 numbers? When it comes to computers, we use a large quantity of numerical values. And in Unicode, we use the number 97 to represent the character A, 98 to represent the character lowercase b, and so on. And that allows us to store or transmit or represent, for one reason or another, the word pig, P-I-G, as 112, 105, and 103. And Nicky has used a much simpler version of that mapping by saying A is 1, B is 2, etc., which gives her the word hello. So a nice way to introduce this idea to students is to do exactly what Nicky did. Walk into your classroom, throw those letters up on the board, and ask students to see if they can work out what you're trying to communicate. And from there, you can dive into this activity, an activity where they can begin sending secret messages to one another using the ASCII or Unicode character set. You give them a table, they can write out their short message, pass that across the classroom to their partner, who will then decode that message by going back the other way. And one of the things it's really fun to do with students that are going to be resilient to doing so is to give them an ASCII table that has been jumbled up so that the letters and the numbers don't line up. And that just emphasizes the idea that you have to agree upon what representation you're going to use. You know, if you think A is the number 106 and someone else is using 97, then the message is not going to make any sense when you decode it. So
then you've got a cryptography activity on your hands.
You have. And so we begin, this ties in with the security discussions and the compression discussions that you can have with students in the older year levels. But it's a really simple activity to start with as young as years 5 and 6. And I mean, you could do it earlier, but year 5 and 6 is where it sits in the curriculum. From a programming perspective, modern programming languages can deal with this. In fact, they don't just have built-in functions that allow you to do this conversion. It also works for emoji. So you can see, that you can plug anything into these odd and character functions in when you're writing code, and you can get the relevant response back. And so, when it gets to the point with your students where they're starting to do some programming, you can take these very, very simple concepts and have them play around with these ideas very, very easily.
So we've got another activity suggestion here, but we don't have either the time or the volunteers to do it. So instead, we'll just give you a shout out. Another really good way of looking at data representation is by using some of the CS Unplugged activities. So this one is looking at image representation and how you can represent that image. We'll talk about image representation perhaps a little bit more if we have time. Otherwise, give us more questions. Similarly, looking at color and how color is how colors are mapped up. Looking at on Adobe, there's a really good way of exploring how colors are represented using numbers, and ways that you can use that to link into further along down the line. Look at compression of images as well. Specifically, when we get to compression, talking about compression later, I'll probably reiterate, but none of the particular compression algorithms are required, but just the understanding that we can use this way of representing information, and that there are different ways of representing that same information that have different benefits.
And I think that's a really nice distinction that we make. The idea that in, P to 6 or a foundation to up to year 6, when you're in primary school, you can explore these ideas and come up with conventions that are a little bit more simplified, that allow the students to understand a concept without worrying too much about exactly how computers do it internally. As you move into year 7 through to 10, we want you to actually start looking at some of the ways computers do these things. But I wouldn't dive into it straight away. Some of the, for example, compression algorithms are very, very complicated. And so understanding the concept of compression is what's ultimately critical here. And you can do that with very simple activities, which we'll be looking at in just a moment. So in year 7 and 8, the major difference is that we specify that we want students to understand the representation of text, images, and audio. And we also introduce a binary representation for the numerical data that's used to represent these things. And they are separate things. So the reason binary is important is because everything that is stored in a computer is actually stored in binary because of the internal hardware. And so everything is represented in numbers, but it's the binary that is actually used to store that inside the internals of a computer. And the thing that I think is absolutely magical about the digital technologies is that we can use two symbols, just a 1 and a 0, and we can model everything in the world. We can represent sound, we can represent images, we can represent text, we can represent interactions between people, we can model physics environments, we can, to some extent, model intelligence and the brain through sort of, some of the artificial intelligence stuff that's going on right now. So, the fact that we can do all of that with just two symbols is pretty amazing. And it's why the digital technologies is such an interesting subject. And it's why we want the teaching of the digital technologies to not focus on specific tools or on specific concepts, but to look at how these ideas have led to the development of the technologies that have had such an impact on our world today. So just reiterating that the fact that we've got these digital binary systems, things that are either on or off, true or false, 0 or 1.
and that we can use those two states to represent everything. This doesn't mean that we expect in this year level for students to be able to look at an image and then give the binary representation of that image or anything like that. It's about understanding those two different concepts, that I can take the word hello and represent that as a number, or even get my phone to answer that. So represent the word pig as a number, and I can represent numbers in binary. Having those two steps quite succinct and quite separate is still fine at this year level. So speaking about binary, there are some fantastic activities, again, on CS Unplugged that we want to spruik for introducing the concept of counting in a binary system. Let's see, am I feeling lucky? So just to show you a really quick segment of this. I hope you guys can hear this as well.
Not hearing it, Nikki.
All right. Well, I will give you a very quick instruction. Each of the bits is either on or off, and you count the number of dots on each of the pages that shows what that particular bit represents. So what they're doing now is asking a student from the audience for a number, and they're trying to represent that number by figuring out whether the bits should be flipped on or off. I will tweet this out later, and I'll send the link. The link's just down there in the corner as well.
Now, if you're looking for ways of exploring binary with students who haven't done it before, that's a really nice way of easing into it. It was written to be used in primary school. It's not required for our curriculum in primary school, but it's very much accessible to students in those younger year levels, and it gives you another mechanism through which you can explore representation. It sets them up very, very well to succeed with that kind of thing in the older years too. So if you've got kids who are finding it particularly interesting and exciting, I would say feel free to introduce it at an earlier age. Now, one of the things that's worth pointing out is that there's an activity available on the Digital Technologies Hub in the Lesson Ideas section called Everything is Numbers that explores absolutely everything you need for data representation in Year 7 and 8, including an activity on sampling sound. And there's not a lot of stuff out there on audio representation that is accessible to students. The sampling sound activity was put together as part of that lesson idea to address that, and it enough information to be able to explore that with or without the binary representation. It's entirely up to you depending on where the students are at. But the activity also points to resources for exploring texts and images as well. Which brings us to
9 and 10, we're getting there.
9 and 10 band. So in Year 9 and 10, we sort of introduce a couple of brand new ideas. Compression, the idea of separating our data from our content, our content from our presentation of that content, and we looked more specifically at how data is structured. And the best way to sort of get you to understand these ideas is through exploring some activities yourselves. So we've linked to those activities, but I'm going to give you a very quick overview to what these actually are. There's a definition for compression in the Australian Curriculum Glossary that is not great. It's one of the things that as authors, we never really got a chance to go back to rewrite in the time that we had. So ultimately what it's all about is working out how we can represent the same information that we're already representing, but doing so using less data. That's ultimately what compression is all about. And students are already great at compression because that's what all of their text speak is, right? The fact that you can write 3 letters and communicate something that is usually communicated through 3 words is a really good example of compression.
There's just so much redundancy in text, Bruce. You need to leverage that redundancy. There's also...
And you're talking about redundancy, look at drawings, right?
Coming back to our pigs. So here's an activity where you can do that same that same activity where we draw a pig or a dog or a cat or a horse or whichever one you'd like, but using fewer lines or in the shortest possible time. And you think about the features that are making this an effective drawing. Can it still be understood? So here we have, here's one I prepared earlier. So in this case, much like our Angry Birds pig, I've abstracted the body away completely, and we have just the salient piggy or doggy features of pointy-ish ears or a snout or a curly tail. And in fact, those legs aren't really necessary either, so we can get rid of them too. So here we've conveyed dogginess or pigginess in very few lines, in a very compressed format. I'm not sure that I would be able to identify the one on the left as a dog and not, say, a cat, given a different question. But in terms of what the important distinguishing features are here in order to represent this information, this is all that's really needed. So the image representation activity that we mentioned earlier as well actually uses this idea of compression as well as just representing images in terms of pixels, whether they're on or off, but looking at this run length encoding aspect. So you can take you can take a larger chunk of an image and represent that as all of this section should be white or all of this section should be black. In fact, that's how a lot of compression algorithms work in terms of why sometimes JPEGs are bigger or smaller, how you can compress them, is doing a very similar thing in looking at what larger groups of pixels can be treated as one big pixel, essentially. So this run length encoding extension from CS Unplugged is a really good one at looking at that concept.
Now, in addition to compression, the idea of structuring data is really, really important once we get to this year level. Understanding what attributes and what relationships between data are necessary to represent that entity in something like a game or in a software application is really, really important. And understanding too the type of data that you're storing, because if we think about phone numbers, we call them a phone number. But the reality is a phone number has a whole heap of extra stuff in it that are not numbers. It's got brackets, a whole heap of punctuation. It can have a plus if you're including the country code. You can format it with spaces or dashes or without. And so it turns out that a phone number is not really a number. And the nature of the data itself is what helps us choose the type that we're going to use to store that data.
I think the best way of representing this or really feeling the truth of it in your gut is when you have a list of phone numbers in Excel and or in Sheets, a spreadsheet editor, and then the formatting is corrupted and they are no longer phone numbers and the leading zeros are deleted and you're sitting there having to manually edit them all. That's when you really feel, no, despite the fact that the word phone number has the word number in it, it's really not a number.
And so, to get a little bit more of a sort of better understanding as to why structure might be important, let's take a little bit of a quick think about how letters work. If you're going to send a letter, and we've chosen letters specifically, you'll see in just a moment, to send your letter, you need to know where it's going, you need your destination, and that has parts like a street and a postcode and a country and all those kinds of things. You need to write the sender address on there. It has some kind of content, the data that you're actually going to transmit. You need a stamp and you need an envelope. So some kind of media to carry it, and the stamp is just sort of passed to say it's allowed to access the system. Now, if we think about how networks work, and we were going to send data through a network packet, you store similar information to you would in a letter. So we've simplified this quite significantly in the example here. But you have a header which contains the destination and the source, so where it's going, where it's from. And then you have the payload, which is the data itself. And what's interesting is you can think of the header as being the stuff on the outside of the envelope. And you can think of the data as being stuff inside the envelope. Now, we intentionally structure the network packet itself to have that information, you know, outside first, inside last, because that allows the computer to know which information is relevant to transmitting the data through the internet, and which information is relevant to, you know, rendering that data on the screen when it's received. And so that's why structure is really important.
It's like looking at the envelope and saying, at the moment, all I need to do is figure out the postcode and then make sure that it gets to that section. And then the actual, the postie will do the figuring out the street address part. But those little boxes on the envelope back in the day allow that information to be identified super quickly. That's what computers are great at, looking at this packet, going straight to where exactly the relevant information for it is, and then continuing on in an efficient manner. Computers are all about efficient manners.
And that structure is what ultimately allows us to do the separation of content and presentation that we want to be exploring with students. So jump back to that slide, Nikki. Yep. When we know how that data is structured, it allows us to store the content in one place and the presentation separately, just like in a sense we stored the presentation information around its location and transmission and stuff at the front and the content at the back. And this allows us to change one thing without changing the other. And that's a really, really valuable thing for our efficiency in terms of being able to process and analyze that data and perform a whole on it. And so there are some really simple examples you can do with students around this. The first is word processing. If students know how to use Word correctly, and if they don't, it's a good opportunity to teach them, then using styles to make all of your headings, say a heading 1 or a heading 2 or a heading 3 or whatever it is that you're going to do, setting all of your headings, and then think of a document that has 1,000 pages in it, has hundreds of headings in it. If you don't use styles and then you decide that you want all your headings to be blue, you have to change each one of those separately. And it's painful process. If instead you've used styles, you can just say, please update heading 1 to be blue, and every single heading updates immediately. And that power, that ability to be able to sort of store that information separately in the computer is a massive time saver. And it's really, really critical for us to be able to sort of process the data in the ways that we do. Which, you know, feeds in nicely to the stuff you might be doing in web development, where we have HTML and CSS technologies specifically for that purpose. And the CSS Zen Garden is a great example. It's a website devoted to the power of CSS, the technology that's used for formatting. Every single website that is visible from that page is identical in terms of its content. Absolutely, like to the letter. What's done is developers have applied different cascading style sheets to change the layout and the formatting to produce very, very different looking sites. I mean, you know, they've changed some of the theming, they've used different graphics, but all of the text is identical. And that's all done without changing the text in any way. It's all done by just changing some of the styling through the CSS. So that's a really fun activity to get students to explore, to play around with. And if they've got some web development under their belt, then they can, you know, give it a go
themselves. Have a go at tweaking some of the designs. It's great. So that leads us to the end of data representation as we have it scheduled for today. We've split up those same data representation curriculum outcomes that we went through on each of those grey slides. And we also have, I really like this table representation. I guess it's a representation of representation. So meta. Just to look at how these concepts, the representation, the different types of data, and compression, how they're introduced in each of the band levels. Just so that we can see that the same concept that's being taught, but just the complexity of that concept is increased as you go up the year levels. There's also a bunch of different connections to other curriculum areas. So there are obviously some fantastic opportunities to work in geography and some data visualization aspects. There are some obvious parallels to the maths curriculum in terms of talking about number systems, place and value. Specifically though, data representation in maths is not the exact same thing as we talk about data representation here. So that's just a little bit of a gotcha. In terms of parallels to art, well, we can have lots of drawings of pigs and dogs all the way through, and certainly have a delightful rant about grammar and language development in English or other language curricula as well. Some nice swap overs. So we just wanted to talk about dogs for an hour. That was the truth, really.
And yeah, if there's one thing we want you to get students to understand, it's that, you know, the development of the representations that we use in our everyday life are all developed by humans. That in computers, we need to essentially convert everything to binary. And since binary allows us to represent any numerical value, whole numbers are ultimately what we break everything down into. And then the reason we do that is it's what allows us to solve problems, to process, to analyze, to do all of the things that we need to do to be able to solve every problem and develop every application we need to write in the digital systems. So teachers are teaching representation and abstraction all the time, in everything you do, in every learning area that you're working in. And this subject gives us some glue, some technical language and terminology that allows us to put some to give those concepts and those ideas some vocabulary that the students can understand. It provides us with a real opportunity to make sure that the understanding that students have about language and about numerical like numbers and mathematics and all of those things is genuine and deep and has a context that makes sense. We don't want students learning things in isolation. This provides us with a means of actually exploring those things in more detail. So thank you for either participating tonight in real time, or to those of you that join us for the recording later on, for setting aside 66 minutes and 40 seconds of your time to listen to us. Please reach out to us with via email, help@aca.edu.au, if you've got any questions at all. We're happy to answer. If it's not Nicky or myself, it'll be someone else on the team. And look out for us coming to a location near you with our workshops that are happening around the country.
Or reach out to
Nicky,
us and we will come to a destination near you. Even better. Yep, just reiterating, thanks for joining us. We desperately want to answer your questions, so send them in. And we will continue exploring curriculum and unpacking different elements of the curriculum over the next few weeks. So let us know which one you want to see next. Great. Thanks.
Thanks, everyone.